ancilla is something that does not contain your useful quantum information. These are like auxiliary qubits in your system. Yeah. So these would be the qubits that you would detect separately, right? So you would measure the parity. So here I'm measuring the parity of these systems. So basically, this guy is going to be either in 0 or 1. This guy is going to be either in 0 or 1. And if I do a control NOT gate, then this should maintain 0 because it will flip this twice. And the same thing happens on these two, on the second ancilla. And if I were to look at the outcome of these ancilla, then 0, 0 would tell me that, like the 0, 0 outcome would tell me that no error occurred here. 0, 1 would tell me that data 3 flipped, so I will like flip it back. And so on and so forth. So this is error correction. So here you would have to measure these guys without perturbing these guys. Sure, but so this is a fault tolerant. So this is like a fault tolerant. So a single physical error cannot cause a logical error. So if there was a single physical error, then I would detect it, and then I would flip that physical qubit back. So that's called a fault tolerant distance 2 code. But there is a catch. And that is, these ancilla are bare, as in like these ancilla are not perfect. They can have their own errors. And if they give me a false positive, then, then even if no error occurred here, I might actually introduce error in my logical qubit. So, so there are theorists who kind of went ahead and like figured out bigger codes where the logical qubit and the ancilla together, like they form a bigger system, like maybe 7 or 9 qubit codes, which can circumvent that problem. And we did not do that, so I'm not going to go into that. So let me tell you what we did. So we chose this code, which is called the 422 or the 412 code. And it's called that because it's, so it encodes, so it uses 4 physical qubits. So in our system, we used 4 out of 5 qubits to store the logical states 0, 0, 0, 1, 1, 0, 1, 1. So there are 2 logical qubits that are stored in this 4 physical qubits. So that's where this 2 comes, and it's a distance 2 code. So it turns out that one of the logical qubit can be made fault tolerant with a bare ancilla. So we have a system of 5 qubits. The 5th qubit forms our ancilla. It turns out that if we encode this and perform this check operations on these encoded qubits, then only the first one out of the 2 is a fault tolerant qubit. And I'll go into the details of that. So just for completion, so if you have a certain basis in which you are defining your 2 qubits, and the basis is this, then the logical operators, for example, if you want to do a Z gate or an X gate on the first qubit or the second qubit, these are the physical gates that you would do on the 4 qubits. So that's for completion sake. You are always supposed to have these operations whenever you encode your logical qubit. Then there are check operations, which are doing controlled X gates or controlled Z gates on these 4 qubits. All right, so we will see what that is all about. Yeah. This is not a full code. Yeah. So, and how will I know that how will I know whether an error occurred? So all of this entire subspace has even parity. So if I had an odd parity, so if my ancilla told me the parity of the first 4 physical qubits and it turned out to be odd, then I will throw that result away. So that's an error. So that we do by measuring all the qubits, and whenever we see the ancilla being 1, we throw that result away. So that is by post-selection we do error detection. Okay. The way you would prepare, for example, the 0, 0 logical qubit is do a Hadamard on the first one, followed by 3 C-naughts that will take you to this state, which is the logical qubit 0, 0. And there can be, while you're doing this operation, so this is a code that circumvents errors that can happen in the encoding step itself. Okay, so what are the cases, what are the channels of errors that can happen? So first of all, like here there can be like a stochastic bit flip error that can happen. It propagates and then it ends up flipping 3 of them, which changes the parity to odd, and it moves out of the space of the logical qubits, and that's an error. But So this guy goes to that, and we discard it. But you can have an error over here on the third qubit, which propagates, ends up flipping both of these guys, and this state goes to the next logical state. So we find that the second logical qubit has flipped, and we don't throw this run because we don't detect it. So it turns out that there are error channels in which the second qubit can be faulty, can have an error. So that's why the first qubit is fault tolerant. The second one, which is sort of technically termed gauge qubit, for whatever reason, is not fault tolerant. So that's why we call it a 412 code. Anyways, so for all the experiments later on, we will be looking at this first qubit and see how fault tolerant it is. All right. For completion's sake, these are the syndrome measurements. So syndrome measurements, in another way of thinking about it, is I'm doing a syndrome measurement where I'm trying to find out if there has been a phase flip or a bit flip on these physical qubits. And if there is a single phase or bit flip, then I will detect that as a change of the state of this ancilla, and I will discard that run. Anyways? Sorry? Previous slide, okay.
Why is that order different here from this?
So the order is important. So these are just like control Z can be done in a control node. Anyways, but this order is different because when you're doing this SZ syndrome measurement, this order ensures that the first logical qubit is fault tolerant. The second one is not. So it just works. If you do the math, then that's how it turns out. Okay. So I will go to the results. First, we prepare the logical state. So this is how you would prepare it. When you prepare it, so this should be 0, 0, 0, 0, 1, 1, 1, 1. So that is decimal state 0 and decimal state 30. So you will see a peak at 30, peak at 1. The yield is 90%. We have 3 C0s here. So there are like efficiencies in the C0 gates. So due to the non-perfect fidelities of the C0 gates, some of those runs give you the wrong outcome. So with a success probability of 90%, we prepare this logical state. And if I look at the populations of the different even parity outcomes, then in the space of the 0, 0 logical state, I get 98% of the population. The most error occurs because there are channels of errors propagating in the second logical qubit. So most errors occur when the second logical qubit flips, and that's what we can see here. But the fault tolerant qubit here has almost an order of magnitude lower error than the other one. So if I were to just work with the fault tolerant qubit, then this is like 0.1 is to 98% error, which is very small. So this is in the state preparation itself. So what we do, a state preparation and then a syndrome measurement. So this is the SZ syndrome measurement where I'm trying to find out the bit flip errors. So I prepare it, and then I find out if there has been a bit flip, and if this ancilla is 1, then I throw that run away. So when we do that, we prepared the logical qubit 0, 0, and then we did both SZ and SX syndrome measurement, and these are the outcomes. These are the probabilities of the different populations that we get. If I throw away all the ancilla is equal to 1 states, then I end up with a very high fidelity preparation of the 0, 0 state. Remember, there are 7 C0 gates here, but based on the error detection, we can throw out the erroneous ones, and we get a really high yield in the logical qubit, the first logical qubit state to be pure. The second logical qubit shows an error because that's not fault tolerant. Okay, so anyways, and because of the imperfect C0 gates, the yield goes down. These are so almost 23% is thrown away, and that comes from all the C0 gates that had an error, and that error showed up in the ancilla. So those were thrown away. So if you had error correction, you would detect that and revert that error. So your yield would not just keep going down. But we don't do that. Anyways. So in the next step, what we did is we tried. Yeah, 5,000. Yeah. So 5,000 repetitions. Out of that, almost 4,200 had showed even parity. So we selected that, and some of them had errors. And turns out that most error was in the logical qubit B, which is not fault tolerant. Logical qubit A is like pretty good. Okay.
Almost looked like you did this and it became worse than the previous step.
Yeah. So what you're seeing here, these populations, are just the raw outcome of doing all of those gates. So all of those gates, right? These states have everything, all the 5 qubit information. Now I take that 5 qubit state outcome, and then I find out which are the ones which showed ancilla is equal to 1, and I throw them away. So that is my error detection, and when I throw them away, I am left with just the logical qubit subspace, and in the logical qubit subspace, I have these 4 states, and I find out what is the yield I have in the fault-tolerant logical qubit versus non-fault-tolerant logical qubit. And turns out that the non-fault-tolerant logical qubit is the main channel of loss. So if this was, yeah.
That number is 1.7?
1.7 and 0.3.
Why are there some reasonable probability around 14, 15, 16? I mean, is there a way to understand? And
Oh.
compared to rest of the values?
Yeah, I have
Like
to.
a factor of 3 or 4.
Yeah, it's higher. I have to go and like look at it closely, but it could have something to do with the kind of the order in which you're doing the gates. These gates are not perfect, and sometimes gates between certain pairs are worse than the others, and it ends up showing as non-uniformity in this, like so. Sometimes short, like it's totally systematic.
I mean, what would be an acceptable thing? I mean, these guys creep up to something like 3% in terms of probability.
Acceptable. So acceptable is so yeah. So that would depend on what you want. But the thing is that most of these are thrown away because there is error detected in the ancilla. So what you're left with, which are acceptable runs, where you assume where you are under where you make the assumption that my logical qubit did not have an error. Like, so this shows if you were wrong in that assumption or not. So that therefore, like these are the numbers that you care about in the end.
Yeah, we're confused about this post
Selection.
throwing away. What does it mean? Okay, maybe
Yeah, you can talk about it.
These kind of post-selection stuff, you will then go ahead and do some analysis on that subset which you think is good, and then qualify it with some quality, right?
Yeah.
It's like yesterday we were talking about parenting by measurement.
Hmm.
You project the state and you throw away all the ones which end up in the excited state. And
Yeah.
then you can go back and say, okay, out of the leftover population, how good or how close to the ground state it is.
Right.
So similarly here, all the ones after you throw out the ones which have error,
Yeah.
the one you select out, is there some kind of post-analysis you do of that subset or that ensemble?
Oh, we don't do any post analysis. So like in the sense like there is no corrections that are made on top of that. So
No,
just
not corrections.
Okay.
That exactly is the 3890 number. So you throw out 5000 minus 4258 and out of the 4258, the correct result was 3890, even indirectly ones, which is supposed to be even. And the rest were supposed to be even, but those are not actually even. According to the ancilla selection, all the 4258 is supposed to be even directly. But out of those, only 3890 actually turned out to be even, and the rest were false. Right? That's what.
so the 3890 actually turned out to be the logical state 00, which is what it should be, and then it leaked into the other logical states, and that is that those are these things. This is also log plot, so it's kind of misleading. So this is actually much smaller than this. Yeah, so 4258 outcomes were still in the logical basis, in the logical subspace. out of which like most of them should still have been in 0, 0, but because there are proper error channels on the non-fault tolerant qubit, they leaked into the second logical qubit flipping subspace. This makes sense.
Basically 0, 0 becoming 0, 1, 1, 0, or 1.
Yeah. So 0, 0 becoming 0, 1, and 1, 1 are like mostly predominant.
Can you detect further which one 0, 1, 1, 1?
Sorry, what?
Can you detect further?
No, we cannot. And that's because we are using one ancilla. So if you use more ancilla, then you will know exactly which one flipped. So after the ancilla tells us that you are in the subspace, those are acceptable runs, we look at the outcome. We measure the 4 qubit states, and from that outcome, we find out how many stayed in the 0, 0 state and how many leaked into the other states. We find out that it leaked into the non-fault tolerant state more than it leaked into the fault tolerant state by almost an order of magnitude. Okay. Okay, so then there are some like theoretical predictions of how the code is going to perform if you had errors introduced into your system. So here's the encoding, and then there are some Pauli errors, which are like identity or X or Y or Z rotations, and assuming that they can happen with an even probability and with weight W. So W says how many Pauli errors that can happen. So there are 4 qubits, there can be up to 4 Pauli errors that can happen with a uniform probability. So what we did in the experiment is we introduced the Pauli error by hand to see how robust the code is. So we introduce it here. So the logical error that you are supposed to get theoretically is basically the probability of having a Pauli error. Once you had that Pauli error, the outcome being acceptable, the probability of that, and then out of that acceptable outcome, what is the probability that you had